Okay. Okay, so for number 3a, we need to show the number of, oh right, for 3a we need to show the number of hybridized carbon atoms that are in the molecule cumin. So there's 6 sp2s and 3 sp3s. The reason being is that the benzene has the benzene which has like 6 of them, 6 sp2 bonds with like the C+1Cs, the benzene ring, and the sp3 from the CH3 that is formed in there. That's where the sp3 came from. There's like 3 of them. Cumin can be synthesized via Friedel-Crafts. Name the mechanism involved. This is electrophilic substitution. Electrophilic substitution because the bromine, sorry, not the bromine, the BrCH2 there is going to be broken down for a bit, and then after that it's going to substitute the H from the benzene ring, and it's going to substitute the H from the benzene ring. That's why it's electrophilic substitution. It's also attacking the benzene ring, so that's why it's electrophilic. On part 2, first step of the reaction forms CH3 2 CH plus atoms. Identify a suitable region for the formation of this cation from 2-bromopropane. For this we use AlBr3 so that the bromine can the bromine can be the bromine can attack AlBr3, and later it will form AlBr4 plus, which is right here, right. But yeah, it'll basically attack the Br from 2-bromopropane will attack AlBr3, and it will make AlBr4 plus, and it will leave the CH2. For B3, complete the figure to show the mechanism for the reaction of benzene. So from the first step over here, we have the benzene ring, and then we have CH3 2 CH plus. The benzene ring will attack the CH3 2 CH plus, and it'll it will donate an electron to the CH3 2 CH plus, and it will make, and then we would go into the intermediate step where the CH3 is bonded with the H. The H here, the H bond with the benzene ring will be broken by the H the H giving an electron back to the benzene, because the benzene ring right now is well, besides the point, the H will give back the electron to the benzene ring, and then after that the final product will be formed right here with H plus as the other product. The Friedel-Crafts alkylation of benzene by 1-bromopropane CH3CH2CH2Br also produces cumene as the major product. The CH3CH2CH2 plus cation formed in the first step quickly rearranges to form the CH3 2CH plus cation. The reason why this is the case, because with this it formed the CH plus. It'll form the second carbocation form. It'll form second carbocation, which is a lot more stable. It's a lot more stable, and it is also positive inductive. Has the positive inductive effect. So yeah, that's why. And then for part C, cumene oxidizes in air to form phenol C6H5OH and propanone CH3COCH3. The reaction is given right here, and we have a table 5.2 to get the standard entropies. First, for C part 1, we need to calculate the standard entropy of the reaction, which we can do by basically the total of the product entropy minus the total of the reaction entropy, which is 146 plus 200, referring to C6H5OH and CHCOCH3, which are on the product side. These two right here, they're on the product side right here, and the reactants being C6H5CH3 and O2, which are on the reactant side. We add this up together, and from this, after you calculate this, we get minus 137 joule per kilomole. Next, show the reaction 1 is feasible at 25 degrees Celsius. To do this, we just need to use the enthalpy change minus the temperature times the standard entropy change. The standard enthalpy change we are given here, minus 371 kilojoule per mole, and we have the standard entropy change up right over here. So wait, right over here we have it, right? We just got it. So we substitute the values in, and then after you calculate, the final result should be minus 330 kilojoules per mole, which means like it's feasible. So over here we have the reaction of phenol reacted can be reacted in two ways with bromine and into the nitrogen chain. Now the bromine here, um, the bromine, the reaction with phenol and bromine will produce this product because OH is wait, we're assuming that hang on. Assuming that the bromine is uh, concentrated, I guess. Since OH is electron donating, it will activate will activate point 2, 4, and 6, and with 2, 4, and 6 being activated, meaning that if you want to attach something into the benzene ring, these points are the ones that are most likely gonna be these points are the points where the thing that you're trying to attach to the benzene ring will be attached. If it's electron withdrawing, they would most likely be placed in 3, 1.3 and 5. In explain why these conditions are different from those for the bromination of benzene. The conditions are bromine water. The reason why it's bromine water is because since OH, as I said, is electron donating, the electron from the O will overlap with the delocalized ring, so that it makes it more possible for more attacks to happen onto the benzene ring. The structure, okay. Draw the structure of Q. Structure of Q, it's already there. And identify organic region R. If we look from or the organic region on S, we have a benzene ring, two ends, junctions, and the phenol ring attached to the nitrogen chain. So with this in mind, we can definitely say that the other region is this right here. We're missing this part. So that means we just need a benzene ring with a nitrogen chain that is not attached to anything yet. That's basically the other region, or the region R. Name the function. Okay. And then after that, we're asked to name the functional group that is formed in reaction 3. The group is simple enough. This group is basically called the azo group. Right. The reaction of phenol with HNO3 produces a mixture of isomers with molecular formula C6H5NO3. Identify the two isomers that are produced in the largest quantities. Now, wait, the reaction of phenol. Reaction, benzene ring. The reaction with a phenol with HNO3. Usually, they would. Hang on. So this would be the process, I would say. So it starts off from HNO3 like this, or HNO2. It's supposed to be HNO2 first. Um, you would you would first reduce HNO3 into HNO2 to make this happen. So HNO2, and then there would be phenol over here. Now HNO2 will give an electron into the benzene ring, which basically just gives the benzene ring or like hang on. So basically it just forms a bond with the benzene ring, and then this benzene ring opens up, turns into this HNO2. Now after this, the H again will give the electron back into the benzene ring, so that the H would be detached from the benzene ring. And then after all of that, it will produce either isomer 1 or isomer 2. Isomer 1, the NO2 is placed in either the 2 or the 6 point of the benzene ring, because OH again is nucleophilic. It donates electrons, so it most likely it activates 2, 4, and 6. Since 2 and 6 is the same thing, but like mirrored, they would be the most major of the two isomers. The other isomer being this one is called 2-nitrophenol. By the way, 2-nitrophenol. The first isomer is 2-nitrophenol. The other isomer is called 4-nitrophenol. Again, it's from the 2,4,6, and this time NO2 is attached on the 4 of the benzene. And then this is the reason the electron will from OH overlaps with the delocalized ring, causing NO2 to bond directly to the benzene because it is more stable. Yeah. Is that do I still have time, sir? Oh. Okay. Thank you.
For number 1A, before we draw the graph, we need to determine whether reaction 2 is endothermic or exothermic. We can see that from this, the color is positive, so we could conclude that the reaction is endothermic. If it's endothermic, draw the delta H facing up. So the shape of the graph would be like this. For B, for experiments like this, usually during the process of the experiment, it will produce carbon dioxide gas. So when the reaction is done, there should be no more effervescence. To calculate the value of delta H1, we use the formula Q equals to mc times delta T. So first you use this formula and then you substitute the value, and you'd get that the value is equal to this. Then right after that, you convert this scalar into the enthalpy by using this formula. But before that, don't forget to find the mole. The mole is 0.04 mole from here. And then you get the answer in joules, because we're asked for the delta H in kilojoules per mole. You divide it by 1000. So our final answer should be minus 34.5 kilojoule per mole. Next, to form reaction 3, this is obtained by using Hess law. So the reactions that is used originates from this table over here. We use reaction 1 and reaction 2, and then we use it to find this equation. So to get 2NaHCO3, you need to multiply everything in this equation by 2. And right after that, you could cancel out the terms that are not needed, like NaCl, H2O, and CO2. When this equation is multiplied by 2, don't forget to also multiply the delta H by 2. Then right after that, you sum this up. Then this will produce the delta H for this new reaction. So the delta H for this reaction is positive 88.9 kilojoule per mole. To deduce the oxidation state of nitrogen in this compound, so we need to know that this compound, it has the total charge of -1. And we know that in this compound it contains 3 oxygen atoms, and we know that the oxidation state of oxygen is -2. So the total oxidation number for oxygen is -6. And since we know that this compound as a whole has this charge of -1, we could conclude that for this compound to be -1, the value of N must be +5. Identify the species that is oxidized in equation 1. So we could see from this reaction over here, the species that is oxidized is Al. Because Al originally started with 0 as its oxidation number, but on the right side of the equation, it becomes +5. To calculate for the enthalpy change in this reaction, since the table is given, we could use the formula delta H equals to the delta H that is required for the bond to break, and minus the delta H for bond formation. So I already drew the bonds. This is the bonds on the left side of the equation, and this one is on the right side. So with that, we could conclude that there are 2 OH bonds on the left, 1 double C bonds, and 4 HC bonds on the left. While for the right side, there are originally 5 CH bonds, 1 C to C bond, 1 CO bond, and 1 OH bond. To make our calculations easier, we could cross it out. Like this one, OH is crossed out with this, and 4 HC is also crossed out with this. So the remaining CH bond on the right side is only 1. So with that, we could plug it into the equation, and then we could plug in the value from this table over here. Then we would get the final answer of -50 kilojoules per mole. Okay.
Okay, so for number 3, this is a neutralization reaction. 2NaOH aqueous plus H2SO4 aqueous. It will become Na2SO4 aqueous and 2H2O liquid. So for the first question, 3A, it asks what's what's the meaning of enthalpy change of neutralization or delta H neutralization. So basically, enthalpy change is when 1 mole of water is formed from an alkali and an acid. That's the basic definition of enthalpy change for neutralization. And for the next question, B, this question asks us to find the amount of H2SO4 neutralized in moles. So first thing we need to do is we need to calculate the moles for every substance, like NaOH, for example. We need to find each of the moles, NaOH, H2SO4, and yeah. So how do we find the moles is we digest from the information above. In NaOH, it's 100, we times it by 10 to the power negative 3, and we times it again by 1. So it will, the moles of NaOH is 0.1 mole. In H2SO4, also the same, we use the same equation and formula. But this time we use the value for H2SO4, which is 75 centimeter cube, times it by 10 to the power negative 3 and 1 also, it will go 0.075 moles. And then after we get the moles of NaOH and H2SO4, and then since it's H2SO4 is neutralized, so we just 0.1 mole divided by 2, and we get 0.05 moles for H2SO4, the amount. And then for II, okay, so for II, we need to find the delta H of neutralization, the enthalpy change, and we need to also to state the units. So for this, we need to find the joules first. So we use the equation MC delta T. The specific capacity is 175, and for the M's is the mass. The mass is 175. The specific capacity is, as we can see here, assume that specific capacity of final solution is 4.18 joules. And for the delta T, we'll calculate the temperature change, which is 7.8. And we calculate this. Wait. And we'll calculate this to get 5,705.7 joules. And then, since this is not the final answer yet, we continue to the equation of the delta H, because the delta H is the question asking it. So delta H will be a negative 5.7057. We divided by 0.1 because 0.1 is the mole amount for NaOH. And then after we calculate this, we will get negative 57.1. The units is kilojoules per moles, because that's the standard unit for delta H. Okay, and moving on to the next question for C. We need to complete the equation of the reaction that occurs when the solution of BaOH2 is added to aqueous sulfuric acid. And we also need to include the state symbol. So basically, how to do this question is basically we just need to balance out the equation first. So just assume that this H2SO4 and BOH is still that there's no value, and we need to find the products first of H2SO4 and BOH. And if we like put these two together, it will result in BaHO4 plus 2H2O liquids, and BaSO4 is solid. And then after that, we just need to balance out the equation. Basically, for this, since it's already balanced, we just put one in each. Suggest why the enthalpy change of neutralization cannot be determined using the addition of dilute sulfuric acid to aqueous sodium barium oxide. Because the precipitate of BaOH2, it also involves in an energy change. So So it cannot be directly determined using the addition of dilute sulfuric acid. Moving on to question 4. For A, we need to write an equation of the reaction of H2O to form an enthalpy change. Basically for this, it's just the normal equation for H2O, which is H2 plus O2 will become H2O. But since this is an enthalpy change, we also need to add half to the reactants of O2. And for 4B, we just need to find the enthalpy change, which is delta H, and to find the formula for delta H, basically energy in, we minus it by energy out. So we just try to identify first the formula, which is this, and then we relate to the table, this table, and then we try to separate first. For example, like B2 or 3. B2, like what's the okay, so usually with these types of questions there is like bonding, for example, like the question number 2, but for this question is much more simpler because they already gave the substance and not the bonding itself. Okay, so we can see just input the numbers. B2O3 is already, they give like negative 1264 kilojoules per mole. So you just input it to the equation, which is energy in minus energy out. So basically B2O3 plus 2NH3. This is basically one like the energy in, and the energy out will be 2Bn plus 3H2O. So you minus energy in minus energy out, and you just input the numbers from the table. So you will get this equation right here, delta H equals to this, and then after you calculate it with the calculator, you will get negative 1126 plus 1356, which results in 230 kilojoules per mole. And now for C. So boron carbide, or B4C, is a hard crystalline solid that has melting point greater than 2000 degrees Celsius. For CI, we need to suggest why the structure and bonding is in boron carbide. So since the melting point is greater than 2000 degrees Celsius, so we can suggest that this B4C is a giant covalent bonding. And for CII, the 100 grams of pure boron carbide contains 78.26 grams of boron. And they asked us to calculate the empirical formula of boron carbide. Okay, so for the empirical formula is basically just the equation is NB over NC. So for NB, we need to find the mass, which is 78.26 grams, and we divide by 10.8, and we also do the same for the NC, which is the mass is 21.74, we divide by 12, as we can see in the previous questions. And after this, we just calculate the equation, and we eventually get 4/1. So 4/1 means like the question asks us basically to just prove why is this equation B4C and not like B2 or C5 or something, because we relate back to the fraction. If it's 4/1, so this means there is 4 B's and 1 C, so it will become B4C. And this is the answer. Number 9. Okay. Okay, for number 9, CHCl3 is another. Okay, so basically, number 9, the question asks us to identify reagent and conditions that can be used to convert chlorine to NaClO. Okay, so reagent and conditions to convert chlorine. The conditions has to be cold, because as you can see, NaClO is made from chlorine in a disproportionation reaction. So the conditions has to be cold in order to convert it, and the reagent has to be NaOH for this reaction. And then for the next question is define disproportionation. So disproportionation is basically just a reaction when the substance is redox, oxidized, and reduced simultaneously at the same time. So what this means is basically they do reduction oxidation at the same time, and not one by one. And for III, we need to balance out this equation. Yeah, we just imagine the box is empty first. We just try to find out from the reactants to products the general equation, and after that we just try to balance out the numbers and values of each substance, and after that we get 3 NaClO into the rest is just 1 and this is 2 NaOH, because we try to balance the values with the reactants with the products. Okay.
Okay. So for number 5 is define enthalpy change of formation. It's actually when a 1 mole of a compound is formed from its elements in their standard states under standard conditions. We should actually mention 1 mole when we want to answer this, because enthalpies are per mole, and we should say form from its elements, because we must start with elements and include standard states. Don't forget, like O2 gaseous state and iron solid state like FeS, O2G, and we should mention standard conditions, which clarifies the enthalpy you mean. And for BI, what to write is Fe2, what is this? Wait. Yes, 2Fe solid state plus G per 2 O2 gaseous state, which we got FeO2 solid state. And for the second equation, carbon, it's Cs plus half of O2G, and we got COG. So the formation enthalpy is always from 1 mole of product, and start with elements in standard states like FeS, and use fractional O2 where necessary allowed. And to use the data in table 4.1 to calculate the enthalpy change of reaction, delta H in kg per mole for reaction 2. So this is the working, and for the first way is to state the method and is using the Hess law, which delta HR equals to delta HF products minus sigma delta HF reactants. And we after that we should list the delta H degree values from the table, which is 824.2 for the Fe, and for the second equation is 110.5 multiplied by 3, because we have 3 carbon dioxide here, and delta H, which is negative 393.5, and we'll multiply it by 3, and we should calculate the delta HR by adding all of them, which like Fe2O3 plus 3 carbon dioxide, which gives 2 Fe plus 3 per 2O3 plus 3 CO2, and the delta HR is 824.2 plus 3 times by 110.5 minus 3 times by 392.5, which gives us negative 24.8 kg per mole if we add it all. And continue to number 10. We given the reaction, which is 4H3PO3 to 3H3PO4 plus 3H3. And we are asked to explain why reaction 1 is disproportionation reaction, and explaining reasoning with reference to relevant oxidation numbers. So for H3PO3 and H, we have plus 1 each, 3 plus 3, because we should times 3 times plus 1 from H plus B plus 3 times negative 2, and from O equals to 0 to P equals to plus 3. And for H3PO4, we have H equals to 3 plus 3, O equals to negative 8, and H plus O is basically equals to 3 minus by 8, which gives us negative 5. And for B we have plus positive 5. And so phosphorus is both oxidized plus 3 to plus 5 and reduced plus 3 to negative 3. In the same reaction, some P atoms lose electrons while one P atom gains electrons. So therefore, the reaction is this proportionation self-redox reaction.